Imagine trying to find your way through a maze, but it's miles underground and you're completely in the dark. For the longest time, that was pretty much the reality of drilling deep into the earth. You just point a drill bit down and, well, hope for the best. But what happens when you need to turn a corner to hit a very specific target?
Yeah, that's the billion-dollar question, isn't it? How in the world do you precisely guide this massive piece of machinery through solid rock when it's so far down you can't see it, you can't hear it, you can't touch it? I mean, it sounds basically impossible.
And for a long time, it pretty much was. But then, this absolutely revolutionary technology came along, called measurement while drilling, or MWD for short. This is the system that acts as the eyes and the GPS for that drill bit, and it completely transformed drilling from a blind guess into a precise science.
So how does this underground GPS actually work? Well, before you can even think about steering, you have to answer the most fundamental question of all. Where exactly are we, and which way are we pointing?
Okay, so MWD is basically a system of tools that are built right into the drill string, sitting just behind the drill bit. It's constantly taking measurements about its own position and its orientation, and then sending that critical data all the way back up to the surface, all in real time without ever stopping the drilling.
All right, let's dive into how this all works. You can really break down any MWD system into 3 essential building blocks. First, the tool has to actually take the measurement way down there. Second, it has to send that measurement to the surface. And third, a system up top has to receive and decode that information so we can make a decision. Let's start with the measurement itself.
That first block is called the Inertial Measurement Unit, or IMU. This thing is really the heart of the MWD tool. It's this incredibly sophisticated package of sensors, specifically accelerometers and magnetometers, that work together to figure out 2 absolutely critical pieces of information: inclination and azimuth.
So the first critical measurement is inclination. To put it simply, this is just the tilt of the well. An inclination of 0 degrees means you're drilling perfectly straight down. As that well starts to curve and build angle, that number goes up, all the way to 90 degrees for a perfectly horizontal well.
So how does the tool even know what its tilt is? Well, the IMU has a set of 3 accelerators all arranged on different axes. Now, they're not measuring speed, they're measuring the one constant they can always feel, no matter what, the pull of Earth's gravity. By sensing how that gravitational force is pulling on each of the 3 sensors, the tool can calculate its exact angle of tilt, its inclination. It's pretty brilliant. But, knowing your tilt is only half the battle. If your well is tilted at 45 degrees, that's great. But are you heading east, west, or northeast? The tool also needs a compass heading, and in drilling we call that the azimuth.
To get that azimuth, the IMU uses another set of 3 sensors, magnetometers. And just like the accelerometers use gravity as their constant reference point, the magnetometers use the Earth's magnetic field. They act like a super sophisticated multi-axis compass, detecting magnetic north to give us the precise direction of the wellbore, even miles underground.
Okay, so now the tool downhole knows its tilt and its direction. That's incredible in itself. But that information is totally useless if it's trapped miles underground. So the next great challenge is getting that message back to the surface in real time. How on earth do they do that?
I mean, think about it. This is a massive engineering challenge. You can't just run a wire. You have to send a signal through thousands and thousands of feet of rotating steel pipe, drilling fluid, and solid rock. It's a tough problem.
The solution to this problem is a process called telemetry. And while there are a few different ways to do it, the most common, the most robust method by far is called mud pulse telemetry. The concept is surprisingly elegant, really. It's summed up perfectly right here. It's basically like sending Morse code, but you're doing it in the mud. The system essentially turns the entire column of drilling fluid that you're already pumping down the well into a high-speed data cable. Here's how it works. The MWD tool has a small valve inside it called a pulsar. To send a signal, this pulsar momentarily restricts the flow of drilling mud. This creates a tiny, controlled pressure spike, a pulse, that travels up the fluid all the way to the surface at the speed of sound. By creating a very specific sequence of these pulses, the tool encodes all that data, the inclination, the azimuth, into a binary stream of ones and zeros. Okay, now for the final piece of the puzzle. A message has been sent from the bottom of the well. We've got data, traveling as these tiny pressure waves in the mud. So what do we do with it when it gets to the surface?
Well, up at the surface, a highly sensitive pressure transducer is acting like a receiver. It's listening for these very faint pulses, and its job is to filter out all the background noise from the rig's massive pumps. It then converts those pressure waves into an electrical signal, which a computer decodes from that stream of binary digits back into meaningful information we can actually use. And the final output is a survey report, which looks something like this. At each station, or measured depth along the pipe, we get our inclination and our azimuth. And using some pretty simple trigonometry, computers can then calculate the true vertical depth, so how far straight down we are, and map the well's precise 3D path through the Earth.
Now, this is the really crucial part. This isn't just about knowing where you are. It's about actively steering the well. This whole process is called geosteering. It allows drillers to make real-time adjustments to navigate the wellbore precisely along the most productive parts of a rock formation. It's like threading a needle miles underground. So let's zoom out and put this all together to see why this technology is such an absolute game changer for modern drilling. It's about more than just steering. It's really about managing uncertainty.
You know, the laws of physics tell us that no measurement can ever be perfect. Every single one of these surveys has a tiny margin of error. And while each error is small, they start to add up with every single foot you drill. Over a well that's several miles long, your actual position could be way off from where you think you are. We visualize this concept as a cone of uncertainty, which you can see right here. The further you drill, the wider that cone of potential error gets. The continuous real-time data you get from MWD is absolutely vital for keeping this cone as tight as possible. This makes sure you hit your target and, just as importantly, you avoid accidentally colliding with any other nearby wells. So when you get right down to it, MWD technology is really what makes modern energy exploration possible. It enables the incredibly complex well paths we need to access resources efficiently. It dramatically improves safety by preventing collisions, and it makes sure wells are placed with pinpoint accuracy, saving millions in rig time and costs.
MWD has already come so far from a simple survey tool to a complex downhole data hub that has transformed the industry. But as its sensors get more sensitive, as data transmission gets faster, and as the intelligence packed inside these tools grows, it really makes you wonder, what new challenges will this technology allow us to solve next? What's the next frontier for drilling intelligence?